In this video, we're going to explore the concept of quantum numbers. Quantum numbers are a set of values which allow us to describe the state of an electron, including such things as its distance from the nucleus, the orientation and type of orbital where that electron can be found, and the spin of that electron. Orbitals and spin are other concepts which we will be discussing in this video. Earlier, we saw that Niels Bohr defined electrons as existing in various shells, and we do not find electrons in locations other than that. This leads us to the first quantum number, what we call the principal quantum number n. Now I know I said that we're going to be talking about quantum numbers, and I just gave you a letter, but what we're going to see is that each of these letters that we talk about, we will be assigning numbers to that have meaning. In this case, quantum number n, the principal quantum number, tells us which Bohr shell we're on. And so we mentioned that all the levels are numbered, level 1, level 2, level 3, and so on. And so when we say that an electron, for instance, is on n equals 1, we're really just saying that that electron exists on the first Bohr shell. If n equals 3, that electron exists on the third Bohr shell, and so on. Now ideally, all electrons would like to exist on the first shell, closest to the nucleus. However, the bottom line is they just can't fit. The electrons will begin to repel each other as they build up there. And so this leads us to saying that every shell, every Bohr level, can hold a total of 2n squared electrons. And so the first Bohr shell can hold 2 times 1 squared for a total of 2 electrons. The third Bohr shell can hold 2 times 3 squared for a total of 18 electrons. And so let's look at all the shells. Here on n equals 1, we said that we can hold a total of 2 electrons. On n equals 2, 2 squared is 4, times 2 is 8. Our third Bohr shell, we just said, can hold a total of 18 electrons. Our fourth Bohr shell, 4 squared is 16, times 2, 32 electrons. Our fifth Bohr shell could theoretically hold 5 squared is 25, times 2, for 50 electrons. For reasons we'll see later, the reality is that the fifth Bohr shell will very seldom ever have that many electrons in it, but that is the theoretical maximum. With all these quantum numbers that we look at, we're also going to look at what we call the allowable numbers for them. In the case of n, our principal quantum number, n can equal integer digits 1, 2, 3, 4, 5, and so on, theoretically up to infinity. However, the reality is that for the atoms that we have discovered, we have found n values up to 7 for atoms in their ground state. The second quantum number we will talk about is quantum number L. Each Bohr shell is broken down into a series of sublevels, which are very close in energy and size. These subshells were named S, P, D, and F. When quantum number L equals 0, that means we're talking about what we call an S sublevel. When L equals 1, it's a P sublevel. When L equals 2, that's a D sublevel. And when L equals 3, that's an F sublevel. Let's take a look now at the allowable numbers for quantum number L. L is able to equal anything from 0 up through n minus 1. And so let's take a look at what that really means. If n is equal to 1, this means that L can equal 0, and that's it, meaning an S sublevel. And so an S sublevel is the only type of sublevel that will exist on the first Bohr shell. On our second Bohr shell, n equals 2, L can now equal 0, which remember is our S sublevel, or it can now equal 1, which would be our P sublevel. Going further, for n equals 3, this means that now L can equal 0, 1, or 2. And so our third Bohr shell could have sublevels S, P, or D. Going out to n equals 4, L can now equal 0, 1, 2, or now 3 for our F sublevel. And so these allowable numbers for L of 0 to n minus 1 show us what sublevels can actually exist at each Bohr shell. Let's look at a diagram of this. As we see on this slide, the number of sublevels that can exist for each energy level equals the value of the principal quantum number at that level. In other words, the first Bohr shell, with n equals 1, can only have one sublevel. And we see that sublevel is an S. The second Bohr shell can split into two different sublevels. And those sublevels are an S and a P sublevel. And so on. Our third Bohr shell can split into 1, 2, 3 sublevels. And those sublevels are an S, P, and a D sublevel. And finally, our fourth Bohr shell can split into 1, 2, 3, 4 different sublevels, being an S, P, D, and F. You'll note that we have a little bit of overlap here with our 4S and our 3D. Don't worry about that for now. We will be discussing that later when we talk about the order in which electrons fill the sublevels, but just note that we do have an energy difference, that technically the 4S sublevel is lower in energy than the 3D sublevel. One of the big reasons that sublevels are important is because each sublevel can hold a different number of electrons. S sublevels hold 1 pair of electrons, P sublevels can hold 3 pair, D sublevels 5 pair, and F sublevels 7 pair. And we see that illustrated in this diagram here. And so we can see here that again, our n equals 1 splits into just one sublevel, that's an S sublevel. S sublevels can hold 1 pair of electrons, we have 2 electrons there. And that makes sense because we said earlier that the maximum number of electrons per Bohr shell is equal to 2n squared. And so for the first Bohr shell, 2 times 1 squared equals 2, and both of those electrons are in our S sublevel. For n equals 2, the maximum number, 2 times 2 squared is 8, and we see that 2 of those electrons reside in an S sublevel in Bohr shell 2. The other 6, our other 3 pair, reside in a P sublevel. And then Bohr shell 3 can split into S, P, and D. 2 electrons in the S sublevel, 6 electrons in the P sublevel, and 10 electrons, 5 pair, in the D sublevel. A total of 18 electrons between the 3 sublevels, which is our maximum allowable number for Bohr shell 3. And then Bohr shell 4 splits into S, P, D, and F. 2 electrons in S, 6 electrons in P, 10 electrons in D, and now we have 14 electrons in sublevel F, for a total of 32 electrons between the 4 sublevels, which is our maximum allowable number for n equals 4. There's a reason earlier, when discussing the number of electrons, that I just talked about them in terms of pairs. That's because within the sublevels, electrons exist in orbitals and 2 electrons can be found in each orbital, 1 pair of electrons per orbital. This is our third quantum number m, or you may see it referred to sometimes as quantum number m sub L. And so an S sublevel, since it can contain 1 pair of electrons, has only 1 orbital. A p sublevel, with its 3 pair of electrons, means there are 3 orbitals, and so on. D sublevels have 5 orbitals, F sublevels have 7. When we look at the allowable numbers for m, we see that m can equal integer values from negative L to positive L. And so in other words, if I'm talking about an S subshell where L equals 0, the only thing that m can equal is 0. And so on. In a p sublevel, L equals 1. So our m values can be negative 1, 0, or positive 1. A D sublevel with L equal 2, our m values negative 2, negative 1, 0, plus 1, and plus 2. And then our F sublevel can have m values negative 3, negative 2, negative 1, 0, and plus 1, plus 2, and plus 3. Now the important part here is not the numbers themselves. The numbers themselves are kind of meaningless to us. What is important is in each instance how many numbers there are. We see that in the case of our S sublevel, we only have 1 allowable value for m. And that leads us to say that in the S sublevel, there is only 1 orbital. In the P sublevel, there are 3 allowable values for m, for 3 orbitals, 5 allowable m values for sublevel D, so there are 5 orbitals, and our 7 orbitals in sublevel F. These orbitals indicate a separate area in space for the electrons to reside. In the S sublevel, we said there's only 1 orbital, and the shape of that is in a sphere. The shapes of these orbitals are a direct result of something called the Schrödinger equation, which is a complex mathematical equation based on probabilities. And so we have 1 S orbital in the shape of a sphere. We said that there were 3 allowable numbers for m for our P sublevel, meaning there are 3 separate orbitals. And those 3 orbitals are aligned along different axes. We have a P sub x orbital aligned along the x-axis, a P sub y orbital aligned along the y-axis, and the PZ orbital aligned along the z-axis. And so if we think about what this does, this means that our 6 electrons that can reside in P sublevels will reside in pairs in 3 different orbitals, which allow the electrons to get as far away from each other as possible, which is advantageous to them since electrons are negatively charged. They want to be as far away from each other as they can get, but still retaining their identity. And then we get even more complicated results from the Schrödinger equation when it comes to D sublevels. We have a total of 5. Most of the 5, 4 of them, are sort of this clover shape that we see here. And again, aligned along different axes. Don't worry so much about the axes that they're lined up on. Just know that we have 4 along different axes of this basic shape, and our 5th D orbital has this shape. I won't show you pictures of the F orbitals as they just get more and more complicated, but know that there are 7 F orbitals, which again allow the electrons to occupy 7 different areas in space. Each orbital can hold no more than 2 electrons. Each orbital holds 1 pair. Each electron in an atom is unique And so we do need a way to distinguish these individual electrons in the orbital from one another. We do this using our fourth quantum number m sub s. Occasionally you might also see this written as just s. This quantum number refers to the spin of an electron. Electrons will spin in opposite directions, and we assign those as either plus 1/2 or minus 1/2. Now again, the numbers there don't mean much other than just that they are spinning in opposite directions. And so a spin of plus 1/2 will be spinning in the opposite direction as a spin minus 1/2. We refer to those as the plus 1/2 as a spin up, negative 1/2 as spin down. That terminology will make more sense in the next video when we start looking at electron configurations. It is important to note that the electrons are not actually spinning on an axis, but rather it's the mathematics of things like the Schrödinger equation, which help us to describe the electrons differently. And so the behavior of the electrons is different, and it's convenient for us to think of that in terms of a spin. And so we think of that as spins being opposite each other. Spin 1/2 or spin minus 1/2. And so, to summarize quantum numbers, n, l, and m sub l will describe an orbital and the location of that orbital. M sub s will then describe the spin of an electron within a singular orbital. A full set of the 4 quantum numbers will describe an electron. Think of it like an address. N might tell you the town that an electron lives in. L will then tell you a particular street in that town. M will tell you the house number on that street. And then S might describe what a single individual within that house is doing. And so we get more and more specific as we move down our quantum numbers. The Pauli exclusion principle also tells us that no 2 electrons in an atom can have an identical set of 4 quantum numbers. And we'll take a look at what that means. For instance, we might be talking about a particular electron that has a set of quantum numbers of n equal to 2, L equal to 1, M sub L equal to 0, and M sub S equal to positive 1/2. And so this means that we're talking about an electron that's in the second Bohr shell. It's in a p sublevel with L equal to 1. It's in some particular orbital in that p sublevel. And plus 1/2 indicates that the electron is what we would call spin up. Now maybe we're talking about a second electron within that same atom. That second electron could also have an n equal to 2, might also have L equal to 1, and M sub L equal to 0. And so that means we're talking about an electron also in the second Bohr shell. It's also in a p sublevel. M sub L is the same, and so we're talking about the same exact orbital. This would mean that M sub S for this electron would have to be spin down, since no 2 electrons in the same atom can have the same set of quantum numbers. We could have a situation like this, though, in which now we're talking about an electron that's in the third Bohr shell. It's also in a p sublevel in that third Bohr shell, and it's in a particular orbital within that p sublevel, and it can definitely have a spin up. But note that even though these 3 numbers are the same, it's a p sublevel in a certain orbital with a spin up, we're in a completely different Bohr shell. And so these would be 3 perfectly valid sets of quantum numbers for a particular 3 electrons within an atom. Something else you might be asked to do is to identify if a certain set of quantum numbers is a valid set or not. For instance, maybe we have n equals 1, and an L value equal to 0, an M value equal to 1, and an M sub S value equal to plus 1/2. And so we'd be asked to find out if this is a valid set of quantum numbers or not. And so we would say to ourselves, okay, well, n equals 1, so that's our first Bohr shell. L equals 0, so that's an S sublevel. So far we're okay because we know an S sublevel can exist in the first Bohr shell. However, our allowable values for M, remember that M can equal anything from negative L to positive L. Here we have an M value equal to 1, even though our L value was 0. And so we would say that this is not an allowable set of quantum numbers. Let's look at another example. Maybe we have n equal to 3, L equals 2, M equals negative 1, M sub S is equal to positive 1/2. This is an allowable set of quantum numbers. None of the numbers here go against any of the allowable numbers that we've looked at. We'll look at one more. Maybe n equal to 2, L equal to 2, M sub L equal to 1, and M sub S equal to negative 1/2. So again, let's think about what these numbers mean. N equals 2 would mean that we have an electron in the second Bohr shell. L equals 2 would mean we have a D sublevel. And so this would be an electron in what we would call a 2D orbital. Now we've said, however, that our second Bohr shell splits into an S sublevel and a P sublevel. There is no D sublevel in the second Bohr shell. The other way to think of that is that our allowable numbers for L are anything from 0 to n minus 1. And so in the second Bohr shell, when n equals 2, our allowable numbers for L are only 0 or 1. Here we have a value of 2. And so this would not be an allowable set of quantum numbers. And so to recap, when we're looking at the arrangement of electrons in an atom, electrons are arranged into Bohr shells, which is quantum number n. From there, we get more specific into subshells with quantum number L. And then within those subshells, we have various orbitals with quantum number M. And then even more specific, we talk about electron spin of the two electrons within that orbital, quantum number n sub s. This slide here gives us a very good summary and overview of all quantum numbers, the allowable numbers, and so on. And so feel free to refer back to it when you're looking at anything to do with quantum numbers. I hope this video has been helpful. I know quantum numbers can be confusing, and so be sure to watch it thoroughly several times if needed, and come see me, one of the tutors, or go to a past session for some extra help.